Hey class. Hey class, welcome to part 2 of lesson 6.5, dividing polynomials. In today's lesson, we're going to take a look at another way of dividing polynomials. Remember, in the last part of the lesson, we looked at long division of polynomials. And in today's lesson, we're going to look at what's called synthetic division of polynomials. So before we introduce this synthetic division, we're going to first take a look at what's called synthetic substitution. And in mathematics, synthetic substitution gives us a way of evaluating a polynomial for a given value of its variable. And it's based around the remainder theorem of polynomials, which we'll delve into a little bit more in this lesson as well. Now, I said that we were going to use this synthetic substitution to evaluate a polynomial function for a given input value. Now, we've evaluated polynomial functions for a given input value before, but we did it in, I guess, the more like traditional, like a natural way rather than synthetic way. We would actually take the value that we wanted to know the output for, and we would actually just simply substitute it in for the unknown and then do all the operations and find out the value. So for instance, with this example A, it says given p of x is equal to 4x cubed plus 3x squared plus 2x plus 1, and they want us to find p of negative 2. So remember that p of negative 2 means that what I'm going to do is wherever I see an x, I'm going to replace the x with negative 2, and I'm going to find the value. So this would be what traditional substitution would look like. We would just go ahead and wherever x was, we would replace it with negative 2. Especially want to encourage you to use parentheses anytime you're substituting into a polynomial, and for sure when it's a negative value you're substituting in. And so I'm just going to go ahead and I replaced x with negative 2 in each and every one of these expressions. Maybe I use my calculator, maybe I do it in my head. I could do this part in my head. I could negative 2 to the third power is negative 8 times 4 is negative 32. Negative 2 squared is 4. 4 times 3 is 12. Negative 2 times 2 is negative 4, so that makes minus 4 plus 1, and that value then for p of negative 2 is equals negative 23. So what that's really saying is when the input x is negative 2, the output will be negative 23. So in other words, the x is negative 2 and p of x is negative 23. Now, the synthetic substitution process will give us that same information. It'll tell us what the value of the polynomial is when the input is negative 2, but how we do it is by a different process that really doesn't involve us actually having to apply exponents to negative 2, which, I mean, sometimes, you know, if we forget to put the parentheses around and we're maybe using a calculator and, you know, sometimes then that can cause us, we can get tripped up by that and maybe get the wrong answer. With synthetic division, we don't even use the exponent. So how do we do that and still get the same value? Well, this is what it looks like. This right here is a synthetic substitution setup. So what exactly does each part of this mean? Well, so what we're planning to substitute in is this part right here, this negative 2. And you can see what we did is we took each of these coefficients of this polynomial, the 4, the 3, the 2, and the 1, and that's all you can see here in this little format. You see the 4 and the 3 and the 2 and the 1. And so how does the synthetic substitution process work? Well, how it works is you take, and you kind of set up this little kind of table format, and you bring down that first coefficient, which is the 4, and then we're going to multiply that 4 by that negative 2. So we'll take that negative 2, multiply that by the 4, and then we're going to bring that product over here into the next column, which was negative 8, and we're going to add it to that next coefficient, that 3, we're going to add to the negative 8, giving us a negative 5. And then we're going to do that same process all over again, This time we're going to take that -2 and multiply it by the -5, and we're going to put it under the next column. And that will be a -2 times -5 is +10. And then we're going to add those two together, which gives us 12. And then finally we're going to do that again. And we're going to take that -2 and we're going to multiply it by the 12, which makes -24. And then we're going to add down that column, and voila, we get that -23. So we get that exact same output of -23, but yet we never had to do any of the exponents at all. And basically what the position that those coefficients in, that 4 being in the first position and the 3 and the 2 and the 1, actually kind of incorporates into that where the exponent would be, because if that's in that fourth position, that must be the x to the third power, and then they work down from there. So there must be really an x to the third here, an x squared, and so on, an x, and then that being the constant term. So it's sort of kind of just built right in that the position of that means that that's what's happening to the input, is it's being raised to the third power, raised to the second power, and so on. And so through this synthetic, which kind of means like an unnatural process, we actually get the same input as we would with natural substitution. So that's synthetic substitution, and we're going to use that same process to do synthetic division. Now, I would like to take a second and show you one more example of synthetic substitution. And so I know you don't have this in your notes, but I'm going to go ahead and just make up one more example and see if I can show you maybe kind of a place where there's a typical pitfall that students encounter, and just kind of head that off at the pass. So here's an example. So let's say I want to do a synthetic substitution to evaluate p of 3 for this polynomial, 4x to the fourth minus 2x cubed minus 5x plus 3. And I probably would have to use my calculator for this if I did traditional substitution, because I'd be raising 3 to the fourth power, and then whatever I get, multiplying by 4, and then so on. But this is how I would do synthetic substitution. First, I take the number I want to substitute in, which is a 3, and then I take all the coefficients from my polynomial. But notice this polynomial now goes from an x to the fourth power, then an x to the third, then down to an x term. And notice that there's a term in there missing, so there was no x squared term. And when that occurs, you actually have to put a placeholder in there, because remember, the position in that table actually represents the exponent that you're having to apply to the input. So in this case, where I see where that x squared term is missing, I'm going to put in a 0. So I'd put in the 4, and then the -2 for the coefficient on the x cubed, then a 0, then a -5 for the coefficient of the x, and then finally the 3. So then, as I did in that last process, I bring down the first number, which is the 4, and I'm going to multiply, and then bring it onto the next column and add. So 3 times 4, that's 12. 12 plus -2 is 10. I'm going to take the 3 and multiply it by the 10, which is 30. Put it into the next column and add. Add 0 and 30, I get 30. Then 3 times 30 is 90. Put it into the next column and add, and that's 85. And then finally take the 3 and multiply it by the 85. And might have to use a calculator there. But actually I think that's 255, because 3 times 8 is 80 is 240, and then 15 is 255. And then finally add the 255 and the 3, that makes 258. And so we get that p of 3 is 258. And we never had to apply any of these exponents at all, but we got the same input as if we had traditionally substituted that 3 in for x and evaluated all of those exponents and coefficients. And you can feel free to pause the video and check that with traditional substitution in your calculator. So now that we've gotten a little more comfortable with synthetic substitution, let's move on to synthetic division. Let's go ahead and take a look at an example of long division that we see in this table here. This is where we took 3x to the third plus 4x squared plus 0x plus 10, and we divided it by the binomial x minus 2. So you can see that we went through that process that we learned yesterday, that long division process of seeing how many times does the first go into the first, and then finding out that that's 3x squared, taking 3x squared and multiplying it by the divisor, which is x minus 2, and then coming up with this part where we subtract, and then so on until we get down to where we can't divide in anymore, because trying to divide x into 50 is not going to work because 50 doesn't have an x. And when we got to that point, we always said, well, then the 50 is the remainder. Well, look in the box next to it, and you'll see an operation that we can use to do synthetic division. This is actually the first part of the synthetic substitution. It's basically what we did was to take what would make this binomial equal to 0, which is 2, and with synthetic substitution, we've gone ahead and used the coefficients from that dividend, the 3x cubed plus 4x squared plus 0x plus 10, and we've done this synthetic substitution, and notice that very last number here is 50, which is the same as the last number here. It represented the remainder in long division. It represents the remainder here, and you'll see these numbers, the 3, the 10, and the 20, these also appear in long division right here. They were the coefficients of our terms in our quotient. So if we were to take and use the synthetic division process, the only thing that would be necessary to do from here on out, once we've done the synthetic substitution, is take these things and interpret what does that mean in terms of the quotient. Well, that first coefficient means that that is the coefficient of a variable that is 1 degree lower than what the original dividend was, which the original dividend was 3x cubed, so this would be 3x squared. And then to go down one term each time. So the next one would be plus 10x, and then plus 20, and then of course that remainder is that 50. So that remainder would be 50 over x minus 2 if we wrote it like that, or we could write it in that form where we say that the quotient 3x squared plus 10x plus 20 times the divisor, which was x minus 2, and then plus the remainder of 50. And that would be equal to the original dividend. So we were able to kind of go through that same process of dividing the polynomials, but using just the coefficients. And then at the back end, we could retrofit those variables back in to really write it as a quotient of those two polynomials. Let's take a look at trying this with another example. Okay, so let's take a look at example A. So they want us to take 7x cubed minus 6x plus 9 and divide it by x plus 5. Okay, so first of all, we can see that there is a missing term in here. There's an x squared missing term, so we could substitute in that place a placeholder of 0x squared. That's always necessary when you're doing synthetic division, to make sure that there's not any missing terms in between the highest degree and the lowest degree. Next thing I want to do is see what would be the value that would make the divisor equal to 0. So we know that x, if it was negative 5, would make that divisor equal to 0. So x equals negative 5 is the number we're going to use and perform that synthetic substitution process. And so this is what it would look like. We would take that negative 5, and we're going to set up that little table. And our coefficients then are going to be from the polynomial 7, and then where that missing x squared term is would be a 0, a negative 6, and a 9. And we could go through that synthetic process where we bring the first term down, which is 7. We're going to multiply and add. So we multiply the negative 5 and the 7, and that's negative 35. And now we're going to add that to the 0 in the next column, which makes negative 35. And then negative 35 times 5 is, so negative 35 times negative 5 is positive 175. Now that sum turns out to be 169. 169 times negative 5 is negative 845. When I add the negative 845 and the 9, I get negative 836. Now what is negative 836? Well, it's not a nice one, but it is definitely the remainder. So that is the remainder. And that means the 7, the negative 35, and the 196 are the coefficients in my quotient polynomial. So how does that doesn't look like a polynomial to me, so I have to go back through and I have to retrofit those variables back in. And so when I do that, I want to go and look at what's the original dividend. It was an x cubed term, and so I know that this one's going to start with 1 degree lower. That's going to be an x squared. Then the next term will be an x, and the final one will be a constant term. Oops, that's kind of getting tight in there. So that would be a negative, no, I'm sorry, 7x squared, and then minus 35x plus 169. Now that is our quotient. Our divisor was x plus 5, and my remainder is 836. So this would be writing it in that form where we have the divisor times the quotient minus or plus, in this case it's minus, the remainder. So if we were to multiply that back out and then subtract the 836, we would end up back with our original polynomial, the 7x cubed minus 6x plus 9. And that would just be a way of checking it. It's not something you probably want to have to do every single time, but say if it was a quiz or test, it would be worth going back through and multiplying that through and seeing that in fact you get back to the original dividend. Let's go ahead and try one more example, and then we'll have you try a few. Okay, so first of all, we'll look at the divisor is x minus a half, and so that means that x value that I'm going to do synthetic substitution with is going to be a half, because a half would make that quantity equal to 0. So I start off with a half, and then I'm going to go look at the dividend, which is 4x to the fourth minus 3x squared plus 7x plus 2, and I can see again there's a missing term. There's actually a missing term at the third power position, so it'd be 0x cubed is going to have be added to this to make a placeholder. And so as I put my coefficients down, I'll put a 4 and then a 0 for that placeholder, the negative 3, which is the coefficient of the x squared, the 7, and the 2. And then I'm going to go through that synthetic process. I'm going to bring down the first term, which is a 4. I'm going to multiply, and I'm going to add to the next column. So 4 times a half is 2. 2 plus 0 is 2. So again, I'm multiplying and adding. So then a half times 2 is 1. 1 plus negative 3 is negative 2. 1 half times negative 2 is negative 1. Add the negative 1 with the 7, you get a 6. 1 half of 6 is 3, and 3 and 2 is 5. And so again, this has a remainder. It does not divide in there evenly, and that remainder is 5. So my polynomial is going to consist of power starting at 1 degree lower than the original dividend, which was x to the fourth, and that means my highest power is going to be x to the third, so this would be 4x to the third. Then that's a positive 2, so that's plus 2x squared, and that's a minus 2, so minus 2x, plus 6, and then of course that 5 is the remainder. So writing that in the familiar form of the divisor times the quotient plus the remainder would look like this. So this would be equivalent to the dividend if we were to multiply that back out. Multiply the divisor by the quotient and add the remainder. And I should apologize if you hear all those weird sounds in the background. That's my dog, and she has found a tasty little bone that she can't let go. So just apologize. Okay, so you might wonder, after learning this synthetic division process, why would we ever go back to long division? With long division of polynomials, although very fun, there was lots of opportunities where you could get tripped up, you could make sign errors, you could make multiplying errors, things like that. Lots of opportunities to make errors. Whereas this process seems pretty straightforward, and mainly it's because you're just dealing with the numbers and you're not having to also juggle the variables until the end, and you just retrofit those back. So why would you not always use synthetic division? Well, synthetic division can only be used when the degree of the divisor, or in other words, you can call it the denominator, I guess if it was written as a fraction, is you can only use it when the degree of it is 1. In other words, when it's a linear binomial or a linear term in some way, that you can use synthetic division. So if I ask this question, can you use synthetic division to divide a polynomial by x squared plus 3? The answer would be no, and that's, again, because the degree is not equal to 1. So the degree of this thing right here is not 1. So it's only legal if your divisor is linear. Now, we've been saying all along we've been using the remainder theorem, and we've been writing our quotients, our quotients of these division problems as in a certain way, where it was the divisor times the quotient plus the remainder, if there was one. And we can use that whole remainder theorem to actually decide if a given term, x plus 3 in this case, if it is actually a factor of a polynomial, in this case x to the third plus 3x squared minus 4x minus 12. In other words, would x plus 3 divide into this polynomial evenly? In other words, is it a factor? Because that's how you know if something is a factor, right? If it divides in evenly. So what we could do is just go about that whole division process, preferably using synthetic division. And then we could see if we got a remainder of 0. A remainder of 0 would signal that it divides in there evenly, so it's a factor. So that's what we're looking for if this is a factor, is a remainder of 0. Which, remember, will be that last cell of our little table. If it turns out to be 0, that means that's the remainder. So let's go ahead and take a look at this problem. So if the divisor is x plus 3, that means that the value of x must be negative 3. And we can set up our synthetic process. I can see that there are no missing terms this time. There's an x cubed, then an x squared, then an x, and then a constant term. So I can just use the coefficients I see listed. So that's a 1. That's the coefficient of x cubed, then a 3, then a negative 4, and a negative 12. And I'm just going to go ahead about my business going through this process, bringing down the 1, multiplying, and adding. So negative 3 times 1 is negative 3. Add those together, I get 0. Negative 3 times 0. I just draw these little things in to help me remind me, which things I'm putting together. Negative 3 times 0 is 0. Negative 4 plus 0 is negative 4. Negative 3 times negative 4 is positive 12. And negative 12 plus 12 is 0. And what that tells me is, yep, since that last number is 0, that means the remainder is 0. And so I could say that, yes, that x plus 3 is a factor of p of x. So it's a factor of that polynomial. So again, what you're looking for when you want to see if something is a factor is you're looking for that remainder to be 0. And in the case of using synthetic division, that means that that very last value at the last column of the sum of the last column of your table is 0. So we'll go ahead and do one more together, and we'll end with number 9 as a you-try problem. So we want to see, is x plus 4 a factor of that polynomial 2x to the 4th plus 8x cubed plus 2x plus 8. And again, I can see here that there is a missing factor, so I'm going to go ahead and put a placeholder in there for x squared. That's going to be a 0x squared. And I'm going to go ahead and set up that synthetic process. With x being equal to -4, because again, remember, we're looking for what makes that divisor 0. So we have -4, and then we're going to set up our coefficients of 2, 8, 0, 2, and 8. And we're just going to kind of run through that process and see if our last column adds up to 0. So bring down the 2, multiply. That's -8, add the column, that's -8 and 8 makes 0. -4 times 0 is 0 again. Add the 2 zeros, I get 0. -4 times 0 is 0. Add the 2 and the 0, you get 2. -4 times 2 is -8. And the -8 and 8 makes 0. So yes, it actually does divide in there evenly. And if I actually wanted to know how many times does it divide in there, so we know it's a factor. It's a factor. And if we wanted to know what the other factor is, we could simply go ahead and take our values here and create that other polynomial that would result. So we know that one of the factors is x plus 4 because we just proved it's a factor. Now the other factor would come from taking these coefficients and writing the polynomial that's 1 degree lower than our original dividend. So that would be 2, and then that's x to the 4, so this would be an x cubed. Then the next coefficient would be 0, so that would be 0x squared and 0x, and that 2 is actually the constant term. And so that actually is the factored form of this polynomial when we have one of our factors of x plus 4, the other one is 2x cubed plus 2. And so if we were to go ahead and multiply those back out, we would see that it equals that original p of x. So go ahead and pause the video. We're going to take number 9 as a you try. If you pause the video, take a few minutes and try that. You can tune back in and check your work, and we'll end the lesson that way. So pause the video now, try example 9, tune back in to check your answer. So thanks for giving that one a try, and hopefully you found out that since the remainder was 6, that x minus 1 was just simply not a factor of the polynomial p of x. Well, that does it for today's lesson, so I'll see you in class.